Welcome to my material science class. This is the third part of an introductory series of videos on the idea of properties of matter or properties of materials. In this video, which is about 15 to 20 minutes long, I'll be using two terms from the previous video where they were explained and defined: stress and strain. So in this video, I'll be looking at, in a little bit of an isolation, how stress and strain interact with each other. This interaction will create two more terms, elongation and elongation percent. So in this video, we'll look at how these four relate to each other. This relationship or this interaction is critical for two reasons. One is it lays the foundation for subsequent concepts in material science. So especially when it comes to strength of matter. So just before we can look at strength, define strength, explain strength, and make sense out of strength, this needs to be looked at. Make sure that you have a crystal clear understanding of the basics on which further stuff will be scaffolded up. Okay, so reason two, this relationship is mathematical. So we'll do a little bit of math, but it's not going to hurt your brain because it's only going to be one subtraction and one division. That's it. Okay, for percentage, multiply by 100. So super straightforward math, about grade 3 level math, but it takes place in the context of this interaction. So before you can proceed with math, you need to have a clear clue on what the terms of this interaction is between stress and strain. Okay, so that comes before crunching numbers. All right, I hope that makes sense. Throughout this video, I'll be using standard Greek letters from the 24-letter Greek alphabet, uppercase, lowercase letters. I'll be using delta to mean subtraction. This uppercase delta, this triangle, and it will be used in conjunction with elongation or deformation. I have both on the previous slide because those are synonyms like elongation, deformation. There it is. Strain will be abbreviated with this lowercase epsilon, and stress will be with this lowercase sigma. They have two lowercase sigmas. This is mid-word, this is word ending. In material science, that sigma is used to mean stress consistently. So, the second thing I want to mention, I will have slides like this, pre-printed slides, where you can, I'm going to be writing on many of these, but my scribblings will not copy from slide to slide, so you will have a good, clean copy of especially the Greek symbols there, or symbols for these physical quantities, because that's how you can, I pre-printed them in a way that will show exactly the same way as it is shown in your textbook, so that way you can relate to your textbooks easier and not be influenced by my scribblings. The context of this interaction between these four terms is exactly the same context as was the context for the previous video, namely materials journey from no load or being at rest, like this push ball here, being at rest, to failure. Everything fails. If it's made of matter, it will fail. It doesn't matter how feeble or how big it is. Spider webs fail, eggshells fail, buildings fail. Bigger things, a mountain can fail. Even bigger things, the whole earth can fail. This galaxy can fail. There are black holes in the middle of this galaxy sucking everything in. But bigger than black holes, the black holes themselves can fail. This whole universe can fail because it's made of matter. If it's made of matter, it will fail. God can fail. Oh no, okay, that doesn't work. God is not made of matter, so. But it was good going until the galaxies and universe. Alright, so if it's made of matter, it will fail. This failure is produced by forces acting on the materials. These forces, or loads, or this stress, so all of those are synonyms. So this stress can be in a number of geometric configurations. It can be pulling, it can be pushing, it can be twisting, it can be shearing it can be bending the material. It doesn't matter how, materials will fail eventually in any one of those geometric configurations. Materials will fail in some combinations faster than in some others, but they all fail. So stress, or this force, is, and I'm just gonna go about green, force or this load or stress is abbreviated by that sigma, and here force is 0, where the material is being at rest. I just get rid of this tool here. So that's what that portion of the line represents. Material at rest, acting on it, no other force other than normal force is the gravitational pull of the Earth, and I'm holding against it, and so the object is at rest. When this force is being increased, and that's what this teal line represents, the material will deform. That's why deformation was on the first slide, or one of the terms. Material will deform there, or elongate, meaning getting longer and longer, or if it's the other way around, getting shorter and shorter, depending on, like I said, in which geometric configurations these forces are being exerted. So this teal line means the elastic range of deformation, where material, when the force is removed, returns to original shape and size. Past this elastic range of deformation, there is the plastic range of deformation. Separating the elastic and plastic ranges is the yield point, at which point, or past which point, deformation is permanent now. Material still may spring back a bit, but it's not going back to original shape and size. So that was also a little bit of a review. What's new is this stuff. The material's original, and I'm not going to use this push ball, it doesn't really work. I'm going to use this chunk of eraser block here, because it kind of looks like this rectangle that I've drawn. So here, where the force is 0 and the material is at rest and there's no stress or no load acting on the material, it has a length at rest. This length at rest is abbreviated as initial length. That reads initial length. Why it's not IL for initial length instead of this, it is LI. It still reads as initial length or length initial. Why the L part is highlighted in it, because the length is important, and that's why I, the initialness of this length, is in the subscript. Okay, so you can read it as initial length, you can read it as length initial, either which way is good. Some people also have length original or original length, but it looks like L0, so I don't like it. But that's the only reason why I don't like. In this video I'll go with LI. So that's what that means. I have here this rectangle that represents this eraser or any object. So it's initial length, and this is why I use this rectangle. I can do this. So whatever its initial length is, it's a number. I don't know, 100. 100 anything, 100 millimeters, 100 inches, 100 miles, 100 spaceships, it doesn't matter. So what I can do with this rectangle is this. I can stretch it like so. As a force acts on it, starting with its initial length, as a stress is being placed on it, or a load is being placed on it, it's getting longer and longer and longer. Under the yield point, when the force is removed, it returns to its original shape and size. But past its yield point, it doesn't. It springs back a little, but it doesn't. So from here on, deformation is permanent. And it stretches all the way until it reaches its final length. That's what's here. Length final. You can. It's not FL for final length. It's length final. It's written like so in material science. So at this point, the material breaks and stops elongating. maybe this eraser or this rectangle, maybe it was 100 millimeters long and now it's 300 millimeters long. So when it breaks, you put the two pieces together and measure it, and it's 300 millimeters. If it's stretching, if it's being crushed and getting shortened, you still have a final length. You measure it, whatever it is, you can measure it. How this looks like in a textbook with a little cleaner imagery, looks like this. Their initial length would be this original rectangle, which has to start here, and final length would be there. So this would be, this whole thing is length initial. This whole thing is length final. See, this length initial might have been 100, just a number. This length final might have been 300 because they kind of look proportionately like just 100 and 300. Okay, and what we have here, this red section, this is the delta L. You can read delta L as delta L. You can say elongation or you can say deformation. Alright, I hope this makes sense. If it started at 100, it got stretched out into 300, then it elongated 200. This delta L equals 200, I hope makes sense. It's fairly straightforward. How it looks like in a textbook is, this is how the same symbols look like in neat print. So again, that's 100, and instead of that rectangle, you know, I want to replace the rectangle with this eraser thing, but instead of stretching it, I have something else in mind. How about bending it this time? You can see that it can be bent, and as it's bent, it's getting longer, especially along this upper side. Alright, after a while some crack lines will appear right here when the bending is the most severe, and then it's going to break in half. So it has its initial length. Here's just a paper tape measure, and however you can measure it at rest. So this would be the initial length, whatever, take a measurement. And when you bend it, it will be longer and longer. Seriously, just measure it longer by 2 millimeters, 5, 10. Maybe at the point when it breaks, it's going to be 20 millimeters longer. So I want to work with the numbers 100 and 120. And in this case, the elongation or deformation or delta L, you can say any of those three things, they all mean the same. That number is 20. And like I said, delta means the business of subtraction. So what was subtracted? Of course, the 100 was subtracted from the 120 to end up with 20. This is how it looks like in a textbook format. This is how it's printed. Length final minus length initial equals delta L. Again, plugging in the same numbers. 120. That's ugly. See, see, this is why I pre-printed these. 120. 100 equals 20 there. So that's how it looks like. Now, because I said math will be on a separate video, so what will be on that separate video? Very straightforward. You see, and this is where it is grade 2 math or so. I'll give you one number and another number to calculate the third one. I think this level of subtraction was done in grade 2 or so. Or in another combination, I might give you this one and this one to calculate that. So math is not hard here. What needs to be kept in mind is that this math highlights what's happening to the material. What is the relationship or the interaction? The story is important. So the stress that's up here on the top of the screen, let me see, do you still have it in view? No, I'm going to scroll up a little bit. There. The story is what this very simple subtraction represents, is that stress is being exerted on the material, and it starts with its initial or original length, and it gets longer and longer and longer, and at fail, so that's at fail, it is 20 millimeters longer than what it was when it started. Alright? That story is captured by this very simple addition. So the skill that you need before you can do math is what's Li and how is it used? What's Lf and how is it used? What's delta L and how is it used? because like I said, I give you two numbers, any two numbers, you need to calculate the third one. So that's math on a separate video. Moving on to strain is what's next. So that's pretty much elongation there. Strain was mentioned in a previous video, and I gave you this definition that strain is the quotient on the elongation and initial length. What does this mean? Quotient means that it's about the business of division. Something will be divided, so you need to be pressing the division button on your calculator. Elongation was just discussed what elongation is, so that's delta L. And length initial was also pretty clear that in this case it was 100. That's the length of material at rest before any load or any stress is placed on it. So how this sentence looks like in a textbook format, because these are words, but how these words look like in a textbook is this. This is what you'll see, either this or this. Both of these say the same thing. Look at this. This is how it reads. Stress is the quotient of, because this looks like a fraction, but every fraction is a division, okay? So strain is the quotient of elongation and initial length. That's how this reads, fairly straightforward. You can see two things in it. That elongation is a smaller part of the story of strain. This is how elongation and strain relate to each other. Alright, this is the smaller idea, that's the bigger idea. This one is part of that one, okay? So in this example, that was 120, that was 100, and that was 20 millimeters, and 20, it needs to be divided by 100. So in this story we can say that strain, the eraser at fail, because this was at fail, the eraser was, at the point of failure, was straining 20 over 100. There, you have a fraction. Or, we can simplify this fraction, 2 over 10. That the eraser was straining 2 over 10. Hey, if you don't like fractions, how about decimals? The eraser at failure was straining 0.2. What does this mean? What this 0.2 represents is the stretchiness of the material. How much it lengthens if it's pulled, or how much it shortens if it's pushed. Okay, how much it changes in length when a stress is acting on it, when a force is acting on it. Okay, I don't want to scroll up again for this character sigma, so I just maybe copy it here. Okay, so force is driving elongation, and this elongation is expressed as strain, how much stretch the material is under at any given point. It could be at failure, it could be halfway to failure, it could be elongating only 5 millimeters, it could be elongating just 1 millimeter. If it's elongating 10 millimeters, then it's 10 over 100, so its strain is 0.1. Or 0.05 if it's 5, or if it's only 1 millimeter longer as it's being bent, it's 0.01 for that 1 millimeter. So at any point during the journey of the material, its strain shows how much stretch the material is under. That's what this is. And this part here is exactly the same as that one over there. You can see that this is elongation. It's just broken up into LF and LI. Now, just because I crossed out those two zeros, that doesn't mean you can cross out here LI. Or, you know, when you have numbers in it, what was it? Final length was 120, initial length was 100, and that's also 100, and that was subtraction. So you cannot just cross out those two 100s just because I crossed out two zeros. That's not how math works. That's why I'm going to put the math on a separate video to make sure there is no stories like this on it. So you want to do your subtraction first and come up with the 20 and then divide it by 100, okay? Again, in terms of math skills, on the math video, look at this. This is still a grade 3 stuff. I'll give you one number and another number to calculate a third one. Very straightforward. Or I'll give you another two and get the third one in any combinations. Those combinations will be shown in the math counterpart of this video. What's important here is how these interact again with each other. How stress is driving elongation and how this elongation is expressed as a number as 0.2. This is 0.2 is a dimensionless number. 20 millimeters was divided by 100 millimeters, so that doesn't have a unit of measure. It's just 0.2. Last item, elongation percent. Elongation percent is the biggest idea of all of these, because elongation percent is the here in this corner, elongation percent here is, you can see, calculated from strain. So you take the strain number 0.2, you times it by 100, you press equal, and you're gonna see 20 on your calculator's display. 20 what? Oh, 20%. Right? What that 20% means, if the razor was 100 millimeters long before bending or stretching or whatever, if it was started at 100, it fails at 120. That's what that 20% means. Now, this was 20 millimeters as delta L. Now, you cannot just take that 20 and make it into a 20% by just scribbling percent sign after delta L. This delta L is elongation and this is elongation percent, but that's not how elongation percent is not made from elongation just by writing the percentage after it. Alright? Think about it. If this was 20, but the initial length is 80, and that's 100, and 80 is the original length. See, 20 out of 80 is now 25%. Alright? So you can't just take this number and just put percent signs after it. Alright? So all of this stuff will be explained in the math video. What's important here is the interaction again. That the smallest idea is length. Out of this length you can make elongation when a force is acting on the material. This elongation can be expressed as, I'm just going to circle that, as strain. When the material is straining, you can come up with a number that shows how much stretch the material is experiencing at any given time, and this strain can be made into a percent just by timesing it by 100, because most people can visualize percentages more than just a number. So that's why they developed elongation percent. Alright, so this story is what's important, that stress is driving elongation. Elongation is part of strain and means how much stretch a material is experiencing, and that can be expressed as a percentage. So again, for math, I'll be looking for understanding of all of these symbols and characters and how these line up, and you need to have this story embedded in your mind before you can do math with these numbers. Alright, the math needs to be preceded by these ideas clear in your head. So that's what I wanted to share. Basically, we're back to this first slide. Thank you very much for watching. There's going to be more math videos on calculating strain, elongation and elongation percent in different combinations. Thank you very much for watching.